What we talked about yesterday. So want to go through the example that we talked about yesterday where we had a scenario, kind of zoom in on this one. We had a scenario where we were looking at a particular, I think it was a chemistry test, where it told us that the scores were normally distributed. It had a mean of 60, so that's where you're seeing right here. Through 60 is the max on our probability density function, okay? Which that probability density function is, give you real quick, you don't need to know this, but I think it helps draw a conclusion or allow us to maybe justify what we are currently going through and the procedure that we're going to go through, how it is actually for us so much more simple than just kind of brute force mathematics. But the formula for this red curve right now is 1 over sigma, which our sigma is 10, times 2 pi times e raised to the negative 1/2 times x minus mu, which mu is 60, over sigma, which is 10, squared. Okay, that is what that red curve is there. Okay, now, that red curve I think we talked about this being like maybe a first period chemistry class has this sigma and this mu. Second period would have a different sigma, a different mu. It's a different sample. Third period would have a different sample. Fourth period would have a different sample, right? So sigmas and mu's per the same maybe test are having different means and different standard deviations. So if I wanted to, or if you wanted to, or anybody wanted to determine probabilities per each one of those courses or classes, they would then have to go through and do what we call a definite integral. Okay, so kind of explain what this is. So we would have an integral here. It's basically an italicized S for finding the integral, which we talked about. And why is it an S? It stands for sums, which we are basically taking underneath this curve a bunch of rectangles and adding them together, right? In those areas. Okay, so that's what this is. And we would go from, in this case, we'd go from negative infinity. Now my tool only lets me go to negative 30, but it's, negative 30 is basically, in this case, negative infinity, or does the same thing that negative infinity does for us. And up to 49. So what we'd have to do is we'd actually have to come up with another, it's called the, we'd have to integrate that formula, which is very difficult, okay, in calculus, and we would have to come up with what the definite integral looks like, and then we would evaluate that definite integral at 49 and at negative infinity, and then we would subtract those two values, okay? But because we're using infinity here, we would have some issue with that, so we would probably, maybe for our purposes, if we were doing this in like a high school calc class, and understanding what this curve is doing and the fact that there's very, very limited area to the left of, like, I don't know, even 30, to the left of 30 is very little area, so maybe we make this, instead of infinity, we make it 30, okay? Regardless, that is a very, very time-consuming process. A lot of arithmetic, a lot of calculus rules, and so forth. And then, if that was first period, and then I wanted to ask the question about second period, I would have to do the exact same thing for second period, but then, in second period, this number right here changes. That 10 is going to change. That 60 is going to change, okay? Because each sample has a different mean, has a different standard deviation. So then I would have to integrate that, and then I would have to evaluate that at the two values that I'm interested in and subtract their difference. That's what integration's about. That is very time-consuming. And I draw a comparison to completing the square. You guys remember completing the square? Yeah. Okay. So what those of you that remember, what does completing the square effectively do for us?
I can't remember. I just hated doing it. Yeah, I hated doing it, so I never remember.
So if I have something like, let's just go, like x squared plus 5x plus 6, and I complete the square on that, let's think. So, do you guys remember the procedure for completing the square?
You start like something to both sides, and then you do something to
Okay, so I'm gonna subtract 6 from both sides. Then I'm gonna take half of that and square it. So that's gonna be 5 halves, so it gives me 25 fourths, right? So add 25 fourths over here, add 25 fourths over here. And what this then does is it creates, does anybody remember what that creates? That's a perfect trinomial. So it creates a perfect trinomial, which allows us then to rewrite the left-hand side as a binomial square. This side over here, so what's that? 6 with a 4, so 24, so negative 1/4 would be that, okay? What this allows me to do then is to use the square root method, okay? And then I can now find the zeros, whether they be real or irrational. I can find the zeros, basically allows me to say, well, x plus 5 halves now is equal to square root of 1/4 is 1/2, right? But this is negative, so it's got an I in it, so it'd be I over 2, it'd be plus or minus. But now x is equal to negative 5 halves plus or minus I over 2. Okay, now usually it's a lot cleaner than this. I just chose random values here. But what allows me to solve for x in that quadratic equation much faster than going through completing the square? That, right? That's a shortcut for it, correct? Okay, so we learn the quadratic formula, and that's what all mathematics is about, is developing rules, relationships, theorems that circumvent arithmetic. Because if I can use this, that goes around all of this, okay? So, going back to our particular situation, we don't want to learn the calculus, okay? And we don't want to go through and follow through with the calculus because it's just time consuming. So what we do is we have this procedure that's called standardizing your distribution, okay? So if I standardize this, so this is a normal distribution, okay? You asked what this tilde means. It means that it has the distribution that is, what did we say yesterday? It was, I got to remember, so it's alphabetical. So it's 60, 10. Okay, so we take that distribution and we're going to convert it down to a distribution that has a mean of 0 and a standard deviation of 1. Okay, and what that allows us to do is removes all the need for our calculus for finding how to find these probabilities for specific or differing samples. Okay. Because if this class has a mean of 60 and the next class has a mean of 65, that's a completely different picture, and it's a completely different integral that we have to find the area for. The formula that allows this distribution to turn into this one is x minus mu over sigma, and that provides us our z-score, okay? So what happens, we talked about this yesterday, we take x being 60, and then subtract that in here where mu was 60 and your standard deviation is 10, that 60 run through there is going to spit out the 0 over there. Does that kind of make sense? Okay. And then if I put 70 in, run 70 through there, x, so 70 minus 60 divided by 10 is going to take that 70 and convert to that 1. So when I do that, then a 65 is also going to get converted, right? And a 65 is going to show up halfway in between 0 and 1. Does that make sense, everybody? Okay, so all your scores that are on this test all get transferred over. Why do we want to know that? Because what has happened is that somebody, don't know who, don't know when, but they knew calculus, and they basically said, if we take this curve right here, and I'm just going to go from negative 30, but the idea is that we're going from negative infinity all the way up to here. And basically what they did is said, okay, if we're going to look at a score of 0. Okay, so it gives me that right there. They did the integral on this curve, and they found that integral, and it should make sense to us the way this is symmetric and it's the y-axis is that axis of symmetry here for this curve. It gives that area to the left of a z-score of 0. So right now, what I'm going to type in here are z-scores. Typed in 0, and we can record 0.5. And then somebody say, okay, well, what if I don't want to go to 0? What if I want 0.1? And they did the calculus, and they get 5.398. Does that make sense? Okay. Well, what if I wanted, instead of 0 or 0.1, but I wanted 0.05? And they did the calculus, and it gave them this. Okay. So these are the probabilities, right? Okay. So what we did yesterday is that we took a z-score of 49. An actual data score of 49, converted it to a z-score using x minus mu over sigma, and it converted to negative 1.1. And we evaluated that, and we saw that it gave us a 13.57% probability that when somebody took, in this group of test takers, if I randomly chose one, there was a 13.57% chance that they scored a 49 or less, right? That's showing up right here in the actual class data, okay? We saw here we put in the 49. Here we standardized everything, put in a negative 1.1. That z-score of negative 1.1 represents that 49, okay? Are these two numbers down here then the same? Does that make sense to everybody? So what happens is that we catalog all of these z-scores and the probabilities that attach to them. And we catalog them in a table that looks like this. Okay? And I have some sites, some URLs I'll give you guys so that you have these. I actually have maybe some, I can print some off as well. Every textbook that you ever go through that's statistic-wise or statistics-based, the back is going to have a bunch of tables like this. Okay? This is called a standard normal distribution table, sometimes called a z-score table. But what this is doing is somebody has cataloged in a convenient way all of those probabilities attached to z-scores from negative 4, essentially in this case, because we can go to negative 3.99. They've cataloged all these z-scores from negative 4 to positive 4 by doing the definite integral. So doing what we just did or what we talked about with that nasty formula, this one back here, okay? They did it however many times to get all of these values that are inside here. Okay, all of these 5-digit decimals are representing probabilities. So what's going on here? We said negative 1.1, right? Negative 1.1, so what we're gonna do, we'll find our z-score, and this column right here is out to the tens place. So negative 1.1, so what that does for us is it allows us to focus now on that row. Does that make sense? So our probability is going to come out of that row, but to decide which one of those that we're going to look at, we go now to this row here, which is going out to the hundreds place. Well, we wanted negative 1.1 on the dot, so this would be that, right? Does that make sense? Okay, attach that onto negative 1.1, and it's negative 1.1 still. So now I'm going to look at this row, this column, and see where does it intersect this negative 1.1 row, and it gives me that number right there. Well, if I zoom in on that number, is that number right there that I highlighted the exact same thing as that area under the curve? Does that kind of make sense to everybody? Okay, so what I'm getting at, and I know that this question would arise at some point. This is why I teach it this way. Somebody would ask, well, where do all these numbers come from? That calculus explanation of somebody sitting down and doing the definite integral of all these is where that comes from, okay? Now, there are some values that we're going to miss out on. Let's say that we did a z-score, and I wanted to know what the score was for somebody that got or the probability for somebody that got a 49.5, okay? So if we went z-score is x minus mu over sigma, but x is 49.5 minus mu, which we said was 60 over 10, that's going to give me 10.5. Divide that by 10 gives me 1.05, right? So the way I do that then, and it's negative in this case, negative 1.05. So I'm going to find negative 1 which is going to be right here. Okay? So it's this. I know it's kind of zoomed out, but we're going to look at that. Whoa. We're going to look at that row. And now I'm going to go out to the 0.05. So I'm going to look at this column right here. I'm going to see where they intersect. And they intersect right there. So the probability, I know it's hard to see, but that would be the price, about 14%. Okay, 14.6%. That's how I would find the probability of somebody scoring 49.5 or less. Does that make sense? All right, and we'll use this table a lot, so I just want to introduce this to you, but we're going to use this a lot, so if it doesn't make sense right now, I will get one of these charts in your hands, and we'll do this for several days. Questions so far? Okay, so if you look at this table, it's only precise. It has a certain degree of precision. I can't go out to thousandths place, right? So what if I wanted like negative 1.15, okay? Well, if I wanted to do that, then what I would basically do is I would take that value there and that value there, because that's negative 1.1 and that's negative 1. Negative 1.01, and this is negative 1.02. So then halfway in between would give me negative 1.05. Does that make sense? So I would take the average of those, and it's going to give me that value that's stuck in the middle. And we'll talk about that kind of stuff later on. But that is all predicated off of calculus. What I need us to really understand is that every one of these, so this curve here, okay, is going to be different for every single situation we come across. Every set of data that we collect, that curve might have a mean of 60, or it might have a mean of 70, and it might have a standard deviation of 8. So you can see how those curves are being able to be changed, right? But every one of those groups of data, however I can change the mean and however the standard deviation works out, every one of those can be standardized, converted down to, or adjusted to fit this one exact curve. And we know all the probabilities of that one exact curve. So then we can ask any question about any other curve if we can reference back to this one. Does that make sense? Okay. Not so much worried right now about our ability to actually do the arithmetic. More worried about, do we understand, once we are doing the arithmetic, what that math really is. Why are we finding these z-scores? And it's to do that standardizing. Okay? We cool with that?
Yeah.
All right.